Hello and welcome back to differential equations. We have section 2.5, non-homogeneous equations with undetermined coefficients. We'll also have variational parameters in this section. This will be a two-part lecture because it's a lot of calculations in here. And I will continue using the same document here, so I'm just going to continue writing and I'll post everything when everything is done. There will be obviously two separate videos on this. So first we're going to start with what is the non-homogeneous equation. That is when we do have a forcing term on the right hand side. So we might have some kind of an y to the n plus an minus 1 y to the n minus 1, right? That's the derivative when you put it in parentheses. It's not an exponent. Plus might have a2 y double prime plus a1 y prime plus a0 y equals to f of x. So it has this forcing term here, which is what makes it non-homogeneous. Now, from before, we know that the solution will have two parts. So y of x would be y complementary of x, which is the part that comes from solving the homogeneous case, and then plus y particular, which is the function that we get from solving the other part that has a forcing term. And you will be, working on two different calculations here. So one calculation is to get the complementary solution, which is could be your constant coefficients, for instance, and then you have exactly, and then you have the particular solution, which will be what we learn now, which is undetermined coefficients, variational parameters, depending on what you guys have. All right, so what is this business of undetermined coefficients? And how does it work? So we are covering only the basic part today, and then we'll have the review and stuff, and then the part 2 of this lecture at some point after the exam. So let's take a look at the basic equation. Y double prime plus 3y prime plus 4y is equal to 3x plus 2. So now we have to work on two problems. So first, let's deal with the complementary solution. What is the complementary solution? Well, for that, we just solved the homogeneous case. So we are ignoring the right-hand side. We'll set that equal to 0. We know immediately that we are supposed to write the characteristic equation. Get values for r from characteristic equation. In this case, we have, what do we have for characteristic equation? What two numbers multiply into none, right? We actually have to, you can't factor this. If they were, if they were swapped 4 and 3, then you would be. We can unleash the quadratic, right, on this one. I can switch the, you mean to fix the equation, make it a minus? Yeah. That will make it much easier. But why simple if we can just suffer? So what we suffer. So let's unleash the quadratic equation on this one. See what's there. So we have 9 minus 4ac. So that will be 16 there. Divided by, holy nightmare is going to be awful. 2. I should have switched the sign. Negative 3 plus minus root of negative 7 over 2. This is absolutely amazing. Look how beautiful this is. It's negative 3 halves plus minus of square root of 7 over 2i. This is beautiful. So y complementary in respect to x is going to be e to the negative 3 halves x, and then we have cosine, sorry, c1. Oh no, we used a. Let's use a. A cosine of root 7 over 2x plus b sine root 7 over 2x. So that's our complementary solution, which is the solution on the left side. Now, and that's old. We know this from before. This is actually how one of the exam questions is going to look like, because we covered this. This is 2.1 and then 2.2 or 2.3 when we did this again. So this was covered in 2 sections so far, and you all should know how to do this without thinking. Like, that's the part. It's definitely something like this on a test, at least one problem like that, at least one. Now we are learning new stuff. New stuff is how to deal with the 3x plus 2 portion of the problem, which is the forcing term, which excites the system and then keeps it moving. So to get this particular part, and then we know that the general solution will be when we add the 2. We examine this f of x equals 3x plus 2, and we assume the solution in form of addition of all of the derivatives of this function. So how many derivatives can I have here? First derivative, second derivative, third derivative, but then they eventually become 0. So f prime is 3, f double prime is 0, and so on. Now, if you stare at this, I assume the solution of the form ax plus b. Because if you look at all of the possibilities that derivatives can take, this is exactly what you see. And the coefficient in front of x could be changing from, level to level. And also the plus 2 is plus 3, then it's 0. Right? So constant term is also changing. So that's why we allow them to change with a and b. It's a little bit tricky to kind of get all of that in the first example, but hopefully the second example will clear much of that stuff. So we were kind of guided to adopt this as a solution, and now we want to determine the value of the coefficients, right? So hence undetermined coefficients until we determine what they are. So how do I do this? Well, this part has to be a solution. And we know what we do with solutions of differential equation. We stuck them in the differential equation, and then we check if they're right. Except this time around, if I put this in a differential equation, I will be able to calculate a and b, actually. So the differential equation is given to us as y double prime plus 3y prime plus 4y is equal to 3x plus 2. Well, I have yp of x. Here I'm going to have yp prime of x, which is just a. and yp double prime of x, which is 0. Plug these in. Plug in. Awesome. Instead of y double prime, I have 0, plus 3 times y prime is just a, plus 4 times ax plus b is equal to 3x plus 2. And now it's like partial fraction decomposition, if you remember that procedure. From this point on, you put all of the a's together, all the b's together, and then compare the coefficients. If you remember from Calc 2 partial fraction decomposition, and you should, maybe I should put that on this test now, so that you can practice and learn. Like anything that is on the test, it's going to be studied. So use sub integration by parts and partial fraction decomposition is good. All right, good to review. So what happened here, guys? Observe. I assumed this type of a solution. This is going to change in every problem, okay? This depends on how this looks like. And you will see that I will do another 2 examples. Every single one will be different, and it will have different this. So you don't get to memorize these. You develop them by taking derivatives until you either hit 0 or you run into a loop, and you see what that loop is. So you keep taking the derivatives. From those derivatives, you figure out what this is. Then you take its derivatives to plug them in a differential equation. Once these guys are in differential equation, the y double prime is 0. Then y prime is a, so 3a. And then y just function is ax plus b, so 4 times ax plus b. Now you will put all together. Make sure that you don't add these because this is 4ax and this is just 3a, so they don't sound the same. So now we put all of these things together. I have 3a plus 4ax plus 4b is equal to 3x plus 2. Now we'll put 4ax first. That's the term with the variable. Then we have a constant term, which is 3a plus 4b equals to 3x plus 2. And here goes the color coding. This term compares to this one. And the blue non-x term, constant term, gets compared to the other one. Identical to your partial fraction decomposition, which you enjoyed in your Calc 2 class. Dare I say that? I did. So now, what we are going to do is say that 4a is equal to 3. Those are the coefficients of x's. And then we also have that 3a plus 4b is equal to 2. You have your system of equations, which in this case is very easy to solve because a is 3/4. And we plug that in there. I mean, I really don't care which kind of witchcraft you're going to use to solve this. Just get it done. So that's going to be 9/4 plus 4b is equal to 2. 4b is equal to negative 1/4. And b is equal to negative 1/16. I hope. Actually, wait, that problem is done in the book. I can cheat. I can just flip and see that I'm right. Yes. So now we have that our particular solution is equal to ax, which is 3/4 x, minus 1/16. The general solution for the entire problem, y of x, is when we add the two solutions. So we had that e to something, negative 3/2 x, a cosine √7/2 x plus b sine √7/2 x And then we have plus 3/4 x minus 1 over 16. Now this is general solution. And if the initial conditions are provided, obviously you take the derivative of this and then you can figure out what A and B are for a particular solution. So this is one of these problems solved completely, and this is actually the cheapest possible one you can get because you have constant coefficients. Yeah, I know it didn't factor, but such is life. And we have a very simple and quick to solve, right, undetermined coefficient part. Now that could have 3 variables or more, right? You get the systems that are horrible, and then right, you sit there and grind through the coefficients, solving a 5x5 system, right? Which is what they do at NGIT and Rutgers. You are actually sitting in this class solving 4x4 on a test, no calculator. That's it builds a character. You know? Let's see another wonderful example. I'm going to jump into homework section because you can read the rest in the textbook. You know all the letters and symbols. I hope. You do? Awesome. I'm trying to ease into this. But unfortunately, they only have 2 modes. Insane and really insane over here. That's okay. Let's do a spicier versions. So this is actually problem number 3 in the textbook. So y double prime, maybe I can denote that, minus y prime minus 6y is equal to 2 sine 3x. So now we have forcing term, which is sine function, so periodically, pushes the system. So think about, you're pushing a kid on a swing, right? It's coming back, you push it, it goes away, comes back, you push it again, and so on. So that's how you apply this. Again, we have our complementary solution, which is for homogeneous case. So to do that, we immediately have r squared minus r minus 6 equals to 0. This one factors. That's nice. R minus 3, R plus 2. And we have R1 is equal to positive 3 and R2 is equal to negative 2. So we are immediately writing the complementary solution in terms of x as ae to the 3x plus be to the negative 2x. So that's that part, the homogeneous part. As I said, problem like this is definitely on your next exam in 2 days because that's the constant coefficients. Now we are ready to work on the particular solution, which is f of x equals to 2 sine 3x. All right, so now what do you do with this? You go and you take all of the derivatives until you reach 0, or if you get stuck in a loop, you will be able to see what are all different functions that you get in that loop. So the first derivative for this is going to be 6 cosine 3x. Then the next derivative would be negative 18 sine 3x. Then the next derivative, third derivative, is negative 48 cosine x. Then the fourth derivative, remember that we are switching notation on the fourth derivative. It's supposed to say 3x there. So that's what, 120, 130, no, 144, right? Oh yeah, it's 54. It's 3 times, yeah, 24 and, yeah, 54. So what do we have, 162 now? The negative from sine, the derivative, right, would cancel the negative that was there. Now, this is way too much. I didn't have to do this many, but I wanted you guys to see that there's the sine, and there's the sine. And they're constantly just having a different coefficient in front, but sine 3x is always the same. And the same is happening with all the cosines. Coefficient in front keeps changing, but cosine 3x remains the same from line to line. So addition of all of these will give us that initial yp that we want to use, which is a sine 3x plus b cosine 3x. So whether it's positive or negative, it doesn't really matter. The entire number is number 2, number 6, number negative 18, number negative 54, number positive 162. So they're all different coefficients in front, but the functions don't change. Sine 3x, sine 3x, sine 3x, and so on. So this a sine 3x is describing every single line that will have sine 3x in it, and this part here, cosine 3x, is for all the cosines. So now I have the particular solution, and what I do with it is I differentiate, plug in the equation, and again do the procedure to find the values. So yp prime is 3x, so 3a cosine 3x minus 3b sine 3x, and we need the second derivative because remember we are plugging this in differential equations, so you have to find another derivative. That's going to be negative 9a sine 3x, and then the derivative sign is cos, so negative 9b cosine 3x. Plug in original equation, and the original equation was y double prime minus y prime minus 6y is equal to 2 sine 3x. Alright, so what do? I replace these where they belong. Instead of y prime, I have negative 9a sine 3x minus 9b cosine 3x. Oh, this is going to be a very long expression. And then we have minus, and now y prime, which is 3a cosine 3x minus 3b sine 3x. Then we have minus 6 times vanilla one, which is a sine 3x plus b cosine x, 3x, sorry. And all of that is equal to 2 sine 3x. Again, collect all of these guys on the pile, all the sines together, all the cosines together, because they all have just different coefficients in front, but they all have the same variable part, or the function part. sine 3x. So now distribute the negative 6. I'm trying to see, do I write this again or just skip all of them? I'll write it. Okay, what else we're gonna do? It's Tuesday, right? Yeah, Tuesday. 9b cosine 3x minus 3a cosine 3x minus plus 3b sine 3x minus 6a sine 3x minus 6b cosine 3x equals to 2 sine 3x. Now in red I have this one. This one has a sign and this one has a sign. So I have negative 15, negative 12. No. Yeah, this one has a b in it, so I'm just going to underline that one twice. So what do I have? I have the ones with a sign. I have negative 15a sine 3x plus 3b cosine 3x. So that's that. And then I have the blue ones. This is the oddball, right? What happened? This one? Yes. Those details that kill the problem, right? Now we put the blue together. We get negative 15 cosine 3x minus 3a cosine 3x, and all of that is equal to 2 sine 3x. So now we factor out sine 3x. So that's the sine. And that's the sine 3x. So those two go together. I have minus 15a plus 3b times sine 3x. And then I have the blue one here. That's not blue. I said blue. I have this one, which would be negative 3a. I'm missing a value here. This is supposed to be a b, right? 15b. 15b, everything times cosine 3x equals to 2 sine 3x. So clearly on the right hand side you don't have cosine, so those coefficients have to equal to 0. I have negative 15a plus 3b is equal to 2, because the coefficient of sine on left side and the coefficient of sine on the right side, they get to be matched. Now I have the other equation, which is negative 3a minus 15b equals to 0. So times negative 5 on the second equation to solve it. So first equation stays unchanged, and the second equation becomes positive 15a. Positive, who chose this number? Equals to 0. Now when we add two equations, we have 78b equals to 2, from where b is conveniently 1 over 36. No, 39. 1 over 39 for B. And then you can go and suffer what A is. So that will be negative 15A plus 3 times 1 over 39 equals to 2. Now these guys will cancel. So I get negative 15A plus 1 over 13 is equal to 2. Move 1 over 13 to the other side. So that's 36, right, times 13 times 2 is 26, right? I don't know if they changed that, so I have to check. You got that. Okay, good. So I have 26 minus 1 is 25 over 13. And we're multiplying both sides by negative 1 over 15 to get A alone. So A is, these guys cancel by 5, you get negative 5 over 39. So I have B and I have A, which gives me the particular solution. So yp of x is equal to, and now we go and we find where it is, A sine 3x. So A sine 3x plus 1 over 39 cosine 3x. So what's the general solution? It's like $20 of gas right there. Yeah, it's 40 bucks out. Yeah. So we have that the solution for this problem is AE to the 3x. I'm used to t's. It's just x is annoying. Plus BE to the negative 2x minus these two guys. And this is how your solution looks like. It's messy. This is actually very easy. This is extremely easy stuff. It's just messy because calculations are long. So you can use it to control people, you know, anytime. Especially when they say, what do you know? You write this out. Ask them to solve a simple second-order constant coefficient non-homogeneous equation using the method of undetermined coefficients. First, check if they can spell that. then if you can do any aspect of that problem, it's okay. I highly doubt they will ever say, what do you know? Because clearly. Right? But we know the secret, right? This is very easy to do. It's just long calculations. It's annoying. You got to worry about those negative signs all of the time. But we haven't done any. I mean, yeah, we actually differentiate. So we did do calculus, right? We did differentiate. So fine, it shows up. But, you know. So all of the problems are always the same. You know, vertical line over here. This is the first part, constant coefficient, so factor or whatever, witchcraft, right? You might have to use the quadratic formula like I did earlier. And you get your complementary solution with your A and B. You can call them C1, C2 if you want. You get to find those if they give you initial conditions, right? This would be the half of the problem then. The second part for the particular solution comes from here, and that's what I said, that every time the YP setup will be different because you get different functions, different combinations of functions. So now what I did is I kept taking the derivatives of the original function f of x, the driving term, right, the forcing term. I kept taking those derivatives until I got bored because I noticed the pattern: sine, cosine, sine, cosine, sine, cosine, with the number in front just oscillating right between different values, bouncing between different values. So what I did is I said, well, this is going to capture all possible coefficients of sine 3x, which is 2, negative 18, 162, and so on. And this b is going to capture all of the coefficients of cosine 3x. Now, we can go forever because they will just keep swapping between sine and cosine. So once we have yp, the form of ip, and this is how you get it. Guys, earlier, I did this, and it didn't make much sense. I kept taking derivative of this until I actually run it into the ground. But now you see, remember how it was coefficients of sine x kept changing? Well, here coefficients of constant terms, right, which is 2, 3, 0. It's captured with b. I know it's 3x over here, but if this was kind of x squared of some kind, then that would change at least once. So you capture those. Once you have the yp, you're supposed to plug it in the differential equations. Your yp is this puppy here. You need that one and that one, so you need to take derivatives. So take yp prime and yw prime p. Take those derivatives, and then just plug them all. Grind through algebra, and do the same thing you did for partial fraction decomposition when you equal the coefficients from both sides. One coefficient side will have a's and b's, the other one will have numbers. So you just get a system of equations, and then you solve system any way you can. And don't forget to actually put the solution together, because the solution is complementary part plus the particular part. Two together give you the overall solution of differential equation. Now, if you have initial conditions, right, you differentiate this, then you plug the, was y at 0, y prime at 0 maybe. You plug those zeros throughout. And well, actually, that's the next problem, which is the last problem for the lecture part. So we're going to enjoy one of these with coefficients. And I want to find, because we haven't done any with e to the x. See you next week. Here's the wonderful one. Problem 32. You're going to love this one. Y double prime plus 3y prime plus 2y is equal to e to the x. Y of 0 is 0. And y prime of 0 is 3. All right, so try this one on your own. What about 17 seconds? No pressure. No problem. You want to walk a little bit? So I see what. Yeah, kind of like that. That's why I don't mind testing out. I haven't done it. Well, coming forth to the international. So if you got to the point, you probably know that it's just a e to the x. I wish that this was, so I'm just going to say, it's kind of looking a little bit weird now because it's just e to the x, right? But if it was e to the 2x, just imagine e to the 2x. The derivatives would be 2e to the 2x, 4e to the 2x, 8e to the 2x, right? So that front coefficient would be changing from 1 to 2 to 4 to 8 to 16, and then you would capture that as a e to the 2x. So now you just put it as a e to the x. And then plow through the problem. You have to have the coefficient somewhere. Wow, this was so close on being the second. Wow. I don't know, but you see that the r is equal to -2 and r is equal to -1, and the exponent on e over there is positive x. That was really close, because it will be repetition. Then you have to multiply by x. We didn't cover that yet. But okay, it works, which is great. So complementary is a, or you can use C1, whatever, e to the -2x plus b e to the -x. So that's the complementary part. Now we're going to go do particular part, so yp calculations. So our f of x is equal to e to the x, whose derivative is always e to the x. So I'm just going to say that yp is a e to the x, whose first derivative is also a e to the x, whose second derivative, sorry, is also a e to the x, and so on. Plug them in your differential equation. So I have a e to the x plus 3 a e to the x plus 2 a e to the x equals e to the x. That would be 6 a e to the x equals e to the x, from where the simple equation 6a equals 1, a is equal to 1 over 6, giving us the particular yp of x to be 1 over 6 e to the x. So now y over x, general solution, is going to be a e to the -2x plus be negative x plus 1 over 6 e to the x. And now we have our two initial conditions. Y of 0 is 0, and y prime of 0 was something, 3. All right, in order for us to solve this, we have to plug in these values everywhere. Well, I need the derivative first, so y prime of x is going to be -2a e to the -2x minus b e to the -x, and plus 1 over 6 e to the x, which remains the same. So plug this one here, plug this one there. Each one of e to the zeros is going to be 1.
Just real quick, does it matter for like a and b at the first part of the
It doesn't.
Like -2 or...
No, it doesn't matter.
Okay.
It was going to be the same. So now 0 is equal to a plus b plus 1 over 6. So we have first equation a plus b is equal to negative 1 over 6. And then the second one is 3 is equal to negative 2a minus b and plus 1 over 6. So that's going to be negative a 2a minus b is equal to 1817 over 6. I'm going to add these two equations immediately because that kills b. I have negative a is equal to, and that's going to be 16 over 6, which is 8/3. So according to my calculations, as they would say, I have negative 8/3. Is this good? Whatever? Oh, it is good? No. And now I calculate b simply by, right, plug that in there. So I have negative 8/3 plus unknown b is negative 1 over 6. So b is equal to negative 1 over 6 plus 16 over 6, which is 15 over 6, which is when you divide by 3, 5/2. Well, I have my a and b now. So the particular solution for the entire problem is negative 8/3 e to the negative 2x plus 5/2 e to the negative x, yep, plus 1 over 6 e to the x. That's it. So that will be a particular solution. Now how do you check this? Clearly take two derivatives, plug in the original differential equation, and then, now that's only if you're interested whether it's right or not. Otherwise don't bother. So this is the solution for the entire differential equation, right here, with those initial conditions. Y of 0 is 0 and y prime of 0 is 3, or 2, or whatever the hell it was. Is it time for review? All right. So let's take 5 minutes, and then we'll continue this lecture next week.